introduction. Good morning, everyone. My name is Vishnu Murali, and I'm very excited to talk about our research on the formal verification of hyperproperties for control systems. This is joint work with Mahati Anand, Ashutosh Trivedi, and Majid Zamani. Cyber-physical systems are systems which have both a cyber component as well as a physical component. Usually, they involve a control algorithm that dictates how a physical process evolves. In recent years, these systems have become more and more ubiquitous. For example, in power grids, medical devices, or autonomous vehicles. Ensuring the correctness of these systems in safety critical applications is an extremely important task. Most of these correctness specifications can be framed in terms of linear temporal logic, or LTL. For example, suppose you want to specify that an autonomous vehicle avoids some obstacles, reaches an objective within some time bounds, it obeys the traffic rules, it does not go beyond the speed limit, etc. All of these can be specified in terms of LTL specifications. Now, the verification and synthesis of cyber-physical systems against LTL specifications have been studied for the past 2 decades. The slide covers just a few examples of the many works in the area, but hopefully impresses upon all of us the importance of this research. Unfortunately for us, there are many specifications which cannot be specified in terms of logic such as linear temporal logic or computation tree logic, such as privacy or opacity. This is because these logics, unfortunately, cannot relate multiple traces at the same instance of time. To overcome this problem, Clarkson et al. Proposed the notion of hyperproperties and studied their corresponding logics, which they dub hypertemporal logics. We all remember the recent hacking of the Colonial Pipeline Company, which forced the company to shut down operations of their pipelines and led to fuel shortages as well as panic buying. The company was also forced to pay a ransom of around $5 million to the hackers. Even more concerning are these headlines from a few years back, which showed how hackers are able to hack into pacemakers to send shocks or hack into Jeeps as it was driving along a highway at speeds of up to 70 miles an hour. So it's important for us to ensure that not only are these cyber physical systems safe and correct, but also that they are secure. And so, as a first step, let us consider the specification of opacity. Here, an outside intruder is able to make some observations on the physical process, but we want to ensure that the observations made by the intruder do not leak some information which is secret. There are many varieties of opacity. For example, in the context of initial state opacity, we want to ensure that the intruder does not learn some information about the initial state. To help concretize this notion, let us consider the grid world example given below. An autonomous vehicle starts from the positions 1, 2, 3, or 4. At the locations 1 and 3 are a bank, and the vehicle moves to a location P, denoting a parking lot, and later stops at a traffic signal T, and then visits these two locations infinitely often. The intruder is able to observe the vehicle only at these locations and is also able to keep track of time. At every time instance, the vehicle moves from one grid location to the other. Now let us suppose that the vehicle initially starts from a location 1 or 3, that is from the bank. The shortest path it has to the location P takes 3 time steps. It either moves north or south and then east twice to get to the location P. On the other hand, if it starts at location 2 or 4, the shortest path to P takes 4 time steps. Again, moves either north or south and then and then west for 3 time steps, and then it lands at position P. Therefore, the intruder, if he is able to observe the vehicle after 3 time steps at location P, can infer that the vehicle did in fact start from a bank location. And so we say that this system is not initial state opaque. On the other hand, let us suppose instead that the bank was locations were 3 and 4. Then if the intruder is able to observe the vehicle at location P in 3 time steps, he is unable to determine whether the vehicle initially started from location 3 or location 1. Similarly, if the intruder observes the vehicle at location P in 4 steps, he is unable to determine whether the vehicle started from location 2 or location 4. And thus, in this new condition, we say that the system is in fact initial state opaque. As one can see from this toy example, these specifications are not very easy, but are important to guarantee. And so our main contributions are that for the first time, we present a sound verification procedure to verify control system against hyperproperties that are specified in the logic hyper LTL. I do emphasize that our approach is sound, but not necessarily complete. And to do so, we make use of the notion of the so-called augmented barrier certificates, which we shall go into more detail as we proceed. First, let's dive into the details by defining the system. We say that a discrete time control system is a tuple of a state set, an input set, and a state transition function. The evolution of the system is given by the following difference equation, which basically states that the state of the system at time t plus 1 is a function of the state at time t and the input supplied to the system at time t. We associate the states of the system to a set of atomic propositions with the help of a labeling function L that maps each state to a set of atomic propositions. For convenience, we make use of sigma to denote the power set of the set of atomic propositions. To ensure that our system is safe, we can use the idea of barrier certificates. For example, let us suppose that the system initially starts from some initial set A, and we want to ensure that it never reaches a set B. Suppose we had a function B such that the value of the function for at every point in the initial set is non-positive, the value of the function is strictly positive in the unsafe set, and we also have the value of the function to be non-increasing. Then, by a simple induction argument, we can infer that no trajectory of the system, starting from the initial set, reaches the unsafe set. Formally, a barrier certificate is a function which satisfies the following three conditions. And if we can find such a barrier certificate, we can guarantee that the system satisfies the LTL formula. SA implies globally not SB. That is, any trace starting from SA will never satisfy SB. With this in mind, let us now have a look at the syntax of HyperLTL and see how things differ. We notice a lot of similarities to LTL, but notice a few differences as well. For example, there exists pi such that phi, or for every trace, for every pi, phi. We use pi to denote a trace variable, and we interpret this as there exists a trace pi such that phi holds, or for every trace pi, phi holds. Similarly, we do not refer to atomic propositions standalone, but rather bind them to a trace variable pi. We make use of a pi to denote that the atomic proposition A refers to the trace pi. The Boolean operators and the temporal operators carry over from LTL, and I would be happy to discuss more about the syntax and the semantics in the question and answer session or offline. But for now, so that we get an intuitive understanding of HyperLTL, let us consider some examples. I use circles to denote positions in a trace, and each line denotes a trace. For example, this is a trace, this is a trace. And so I say that A pi is satisfied by the set of traces if the trace corresponding to the variable pi initially satisfies the value of A. To show how hyper LTL can relate different traces, let us consider the example in the right. The formula we consider is A pi 1 until B pi 2, which indicates that along trace pi 1, the atomic proposition A must hold until such a point where the atomic proposition holds B holds true in trace pi 2. If we consider standard LTL semantics of A until B, then this must hold along the same trace and not along different traces. This is one of the key points about hyper LTL, which allows us to relate how different traces influence each other. Hyper LTL also allows us to quantify trace variables. For example, let's consider this last specification. This reads as follows. For every trace pi 1, which initially satisfies the atomic proposition A, there exists a trace pi 2 such that in the next time instance, B is true along trace pi 2. So let's start with a set of traces. Well, For this trace, it initially satisfies A, and there exists a trace, the second one, so that it satisfies B at the next position. So these pairs satisfy the property. Similarly, the second one satisfies this property trivially as it does not initially satisfy A. Third and fourth, similar to the first and second, satisfy the property. And so we can say that this set of traces do satisfy this hyper-LTL example. Now let us have a look at a security policy which can be specified in hyper-LTL, namely that of non-interference. This property states that if two traces agree on the observable inputs, then the two traces must also agree on the observable outputs regardless of the hidden input. That is, we want the system to be opaque with respect to the hidden input. Formally, we specify it as follows, and it reads, for every trace pi1 and for every trace pi2. If the two traces pi1 and pi2 agree on the values of the input I at every position, then it must be true that the two traces pi1 and pi2 also agree on the value of the output. And this brings us to our key problem we study. Given a system, a labeling function, and a hyper-LTL specification, we want to decide whether the system does satisfy the hyper-LTL specification. For convenience, we assume the hyper-LTL specification phi to be of the form mu1 pi1, mu2 pi2, and so on up to mu p pi pc, where mu I denotes either the existential or the universal quantifier. For example, p can be for every trace pi1 that exists pi2, and so on up to for every trace pi pc holds. And so, to help reason about this, we consider the p-fold composition of the system with itself. The p-fold composition of the system with itself can be thought of as a system whose state set and input set are the PRE Cartesian products of the state and input set of the system, while the state transition function can be thought of as the component-wise transition. We extend the labeling function L to map a state in this composed system to a p-tuple of a set of atomic propositions. We also make use of X tilde to denote a state of the system and X naught tilde to indicate the initial state. And so we consider the main challenges as we work our way towards guaranteeing the satisfaction of a hyper-LTL specification. The first challenge we face is that we want to ensure that the selection of actions in the composed system do in fact correspond to the selection of traces in the initial system. The second question we consider is, we know that barrier certificates are guarantees of safety in the context of LTL. So what corresponding hyperproperty do we guarantee with respect to our augmented barrier certificates? Lastly, how do we make use of these augmented barrier certificates to guarantee the specification of an arbitrary hyper-LTL specification, to guarantee the satisfaction of an arbitrary hyper-LTL specification? So let's work our way up this pyramid by first showing that it is true that the selection of actions on our composed system do in fact correspond to the selection of traces. To do so, we think of two games. The first is a game of checking the validity of a hyper-LTL specification. And this is a game between two players, the existential player, Eloise, and the universal player, Abelard. For convenience, let us consider the hyper-LTL specification that exists pi1 such that for every pi2 there exists a pi3 such that C holds. When the game starts with Eloise selecting a trace sigma 1 as the value of the variable pi1, Abelard then selects a trace sigma 2 as the value of the trace variable pi2, and lastly Eloise selects a trace sigma 3 as the value of the trace variable pi3, and the game ends. We say that Eloise wins the game if the tuple sigma 1, sigma 2, sigma 3 satisfy the property C. We say that Eloise has a winning strategy if, regardless of the choice of sigma 2, she can always ensure a selection of traces such that those traces satisfy the formula. And if she does have a winning strategy, we say that the hyper-LTL formula holds. We note that the selection of trace sigma 2 may depend on the value of the trace sigma 1. And similarly, the value of the trace sigma 3 may depend on the value of sigma 2 and sigma 1, but not the other way. Sigma 1 cannot depend on the values of sigma 2 or sigma 3, and similarly, sigma 2 cannot depend on sigma 3. Equivalently, we think of a game on the p-fold composed system. In our case, in this example, we consider on the three-fold composed system, we initially start from the state x naught tilde, and the game proceeds with the player's LOEs and Abelard selecting actions. Initially, LOE selects an action U1, Abelard selects an action U2, LOE selects an action U3, and then the system evolves based on this three tuple to the next state. And this game proceeds indefinitely, resulting in an infinite trace being generated. However, the key point is that Eloise's choices of actions U1, U2, or U3 depend entirely on the current states and choices resolved before her. Her choice of action U1 cannot depend on U2 and U3, and her choice of action U3 depends on U1 and U2. Therefore, we arrive at the following lemma. If Eloise has a winning strategy in the turn based game, then she in fact has a winning strategy in the stage based game to guarantee the satisfaction of a specification. And so we can argue about the satisfaction of the specification in terms of the composed system. We thus have the first base of a pyramid, and now we can consider what's the equivalent analogy in the context of hyper-LTL. We call a property chi a conditional invariance property if it is of the form mu1 pi 1 up to mu p pi p. Globally, if SA is true, it implies that globally, not SB is true. This is quite similar to the LTL property guaranteed by barriers, except we have a quantification preceding this. We also note SA and SB can be Boolean combinations of atomic propositions. Based on this, we define an augmented barrier certificate as follows. That is, given the LTL, given the conditional invariance specification and the sets A and B, we define the barrier to be non-positive for all states in A, positive for all states in B, similar to how we define it in the case of barrier certificates. But lastly, the last condition, we make use of a quantified set of inputs to dictate how the composed system evolves. And so we have the existence of an ABC implies that the system satisfies the conditional invariance property. Thus, we have the analogous definition of barriers in the context of the composed system, and so we can guarantee that systems can satisfy conditional invariance properties. The last step is the question of how we extend this to guarantee the satisfaction of an arbitrary LTL, hyper LTL specification P. To do so, we construct an implicitly quantified Buki automata, that is an NBA, corresponding to negation C, where the alphabet of the automata is sigma to the power p. That is a p tuple of a set of atomic propositions. This automata also has a set of states, an initial state, a transition function which maps an input set an input state, and an alphabet to a set of states as it's a non-deterministic automata, and a set of accepting states. A word is accepted by this automata if the corresponding run of the word on this automata visits an accepting state infinitely often. We note that a word is a member of sigma p to the omega, or we can think of a word of this automata to be a p tuple of traces. And with this, we arrive at our key result. To show the satisfaction of arbitrary specifications, we take the implicitly quantified Buki automata and then identify all lassos that start from the initial state Q0 and cycle on some accepting state QF in F. A lasso is a simple path from Q0 to QF, followed by a simple cycle from QF to itself. We decompose these lassos into consecutive transition pairs, which we call SAI and SBI. Now, each of these pairs represents some conditional invariance property. If we can find a suitable augmented barrier certificate for at least one transition pair along every lasso, we can guarantee the satisfaction of the specification. And this is as follows. This augmented barrier certificate acts as a scissor which disallows the p tuple of traces from satisfying SBI at any point in the future if they satisfy SAI. However, for these p tuple of traces to satisfy the negation C, they must satisfy SAI and at some point in the future must satisfy SBI for some transition pair. Therefore, we note that the existence of this augmented barrier certificate implies that Eloise has a strategy such that she always can satisfy C, and therefore we can infer that the system does in fact satisfy the hyper-LTL specification. In summary, given a control system S and a hyper-LTL specification P, we construct the p-fold composed system S to the P and the NBA corresponding to the negation C. We find augmented barrier certificates on this NBA, and if we can find such an augmented barrier certificate for some transition pair along every lasso, we infer that the system does satisfy the specification. Otherwise, we cannot conclude that the system does not satisfy the specification, as we give a soundness guarantee but not a completeness guarantee. We then turn to the problem of how we synthesize or find these functions, which are augmented barrier certificates. And so, under the assumption that the state set and the input set are continuous set, that the system evolves based on polynomial dynamics, the sets X and U, as well as the sets A and B with respect to the conditional invariance are bounded semi-algebraic sets. That is, they can be represented in terms of polynomial inequalities. We can make use of the technique of sum squares to find these augmented barrier certificates. This formulation may not seem very intuitive, but the first line basically corresponds to the first condition we had, the second to the second condition, and the last to the last condition of augmented barrier certificates. We then verify this with the help of case studies. The first is to verify delta approximate initial state opacity of a vehicle system. Its state space corresponds to its position and its velocity. And we want to ensure that for any trajectory of the vehicle that begins in a secret state, there exists a trajectory that begins from a non-secret state such that there are observations. In this case, the intruder can observe the velocities are delta close to each other, with delta being 0.15. To do so, we consider a set of atomic propositions as follows, and the hyper-LTL formula phi, which reads for every trace by 1 such that the trace begins in a secret state, there exists a trace by 2 which begins in a non-secret state, and these two agree on the outputs or the output or the velocities, the velocities of these two are always delta close to each other. We construct a corresponding NBA represented here and find an augmented barrier certificate for the pair A1, A2, and A3, A3, and A4, A4. We do not consider the transition A1, A1 as we assume that the virtual copy of the system, that is the second trace by 2, starts from a non-secret state. With this, we find an augmented barrier certificate to guarantee that the hyper-LTL specification is satisfied. We also show the results of our simulations. V1 indicates the velocity along the secret state. V2 indicates the velocity along the non-secret state. The region in blue indicates when they are more than delta far apart. And we know that along the trajectories, the velocities are not more than delta far apart. Similarly, we consider the initial conditions, the initial positions of the vehicle. X1 indicates the secret positions. X2 indicates the non-secret positions. We also consider the case study where we verify the initial state robustness of a temperature control system whose dynamics are given as follows. And we want to ensure that if a trajectory starts from the initial state, x3, remains safe, then every trajectory that starts from a delta close set to this, given by x4, also remains safe. We again consider a set of atomic propositions, AP, and the hyper-LTL formula, which reads, for every trace by 1 and for every trace by 2, if it is the case that pi1 starts from the initial set and pi2 starts from a delta close set to this initial set, then both these trajectories are always going to be safe. We construct the NBA and find an augmented barrier certificate for the pair A2, A3 and not A1, A1. We find the augmented barrier certificate, and we also show by simulation that these trajectories do not reach the unsafe set, where the value of the temperature value will reach 25. In conclusion, we provide an automated theoretic approach for verifying discrete time control systems against hyperproperties. We introduce the notions of augmented barrier certificates to provide conditional invariance guarantees, and we made use of the sum of squares technique to synthesize suitable augmented barrier certificates. As future work, we plan to investigate the synthesis problem as well as investigate the verification problem for other classes of systems, such as stochastic systems. Our work has been supported by the National Science Foundation, the NSF, and the German Research Foundation, the DFG. Our full paper is on arXiv at the following link. Thank you very much for your time. I would be more than happy to answer your questions.
Thank you, Vishnu. Any questions for Vishnu? All right, there is one. Kaushik.
Hi, thanks for the nice talk. So I was just wondering, so this is all for conditional invariance because you are using barrier certificate. So is there some equivalent extension to conditional liveness or something like that?
That's a good question. Allow me to put it this way. For now, barrier certificates gives us the guarantee of invariance. So the question is, what equivalent property do we consider in the case of liveness? In particular, if you want, the problem of conditional invariance is actually a bit different from the problem of hyper safety in the context of hyper LTL. So it's something we would investigate in future work, or at least it's definitely things which I'd like to look at. But right now, I do not have an answer of what's an equivalent property you can consider as.
So what comes to my mind is like Lyapunov function. So I was wondering if there is some augmented Lyapunov function that will be something to try.
Yeah, no, you're right. Definitely will be a good question to look at. But
but one thing I should add, I don't know what is the definition of hyperliveness, but this method, as Vishnu explained, can go for hyper LTL. So if the fragment that Kaushik you are saying is not part of hyper LTL, then yeah, this method, so far this technique cannot handle, but this technique can handle general hyper LTL by mainly working with the negation of the formula. Yeah.
Oh, I see. Okay. I see. Okay.
So it provides a sufficient condition by not reaching the accepting state or not looping over the accepting state in the negation of the formula. Therefore, we can verify the property holds. Of course, this is sufficient, not complete approach. Yeah.
I see. But this is a deterministic Biffy automata or
non-deterministic? Non-deterministic. The transition function is to the set of.
Okay. Yeah. Right. Okay. Thanks.
Right. I don't see any other hands, so thanks again, Vishnu. So